which is a planet somewhere in our galaxy out there. And he's just published a book with all kinds of pictures and all kinds of texts about that contact he's had.
A Swiss farmer named Billy Meyer. Meyer has hundreds of other photos and some metal fragments from the spaceship. The photos that are not in the current book are still being tested, and so are the metal fragments. Marcel Vogel, a research scientist with IBM, tells us about one piece of metal that he examined under an electron microscope.
It's a very unusual combination from a metallurgical standpoint. I've shown these to metallurgists, and they shake their heads. And the most unusual thing is the purity of these metals in adjacency to one another without their cross-contamination. They're very sensitive to light, and as soon as I expose them to intense light from my microscope, the metal oxidizes very rapidly and just breaks down. I've never seen that. This really took me back. That only happened on Friday. And then going back in tonight, I'm having another go at observing and measuring that.
Okay, Dr. Vogel, could you tell us about your background briefly?
Good. I'm a senior scientist with IBM in the General Products Division laboratories at Monterey and Cottle Road. My work has been from earliest childhood in the study of the conversion of energy inside of crystals. I started at the age of 7 on the exploration of bioluminescence, the firefly, the light of the firefly, and by 11 I was synthesizing the chemical that made the firefly glow, the 3-amino-phthalate 1,4-dione. It's a chemical analog to that which is in the firefly, and from that point on I've focused my life on the study of luminescence, the conversion of energy in crystals. The materials that are in your color television, that are fluorescent lamps, and built my own corporation in this, and then developed for IBM the magnetic disk coding memory system, which now IBM uses throughout the world in their disk memories. I've developed the coding. We hold the basic patents for this material, and I've been into the field of material science all of my life. For the past 20 years, since 1960, I've developed a skill in optical microscopy because I wanted to study liquid crystal systems. I said there would be a very important new discoveries made in liquid crystals. These will be useful in watches, display devices, and I proceeded to develop these materials for IBM. With that, I have put together probably the most complete optical microscopic gear, about almost $250,000 in optical microscopes. And this brings us to the present point where I was contacted in April by Mr. Jim Delatosa, and they told me about this unusual sighting in Switzerland by Mr. Myers. I've had a rather negative feeling towards UFOs because I said, unless I have something physical that I can get my hands on, just reported sightings and things like that have no interest to me. And from a human interest standpoint, I said, fine, I'll see what I can do to investigate these specimens that were left by these contacts. And so Mr. Delatosa contacted Mr. Stevens, and he wrote to me the letter and sent me 3 specimens.
And did you analyze all?
Yes, I did. If you want now, I can show you some of the results that we got with the first specimen that was given to us.
It is silvery, as you can see, in color. It looks like it has been melted. This is the raw specimen which was mounted in plastic, lapped and polished in Switzerland. And now you can see this metal in its pristine state. It is remarkable. We will now illuminate it by oblique illumination. has many facets of color to it. Taking out the analyzer to bring out some more of the metallic sheen and luster to it. As one goes to higher magnifications on this specimen, one will see other fascinating details. This type of research takes many hours to fully exemplify. We'll look at the backside of this specimen now. This is the backside of the specimen, and under cross-field polarized light, one does see these white crystalline birefringent deposits. The luminous area to the right is just a reflective glare from the light source, as one can see here, but we're dealing now with polarized light, and there is this area illuminated. One side is highly metallic, the other has some forms of crystalline occlusions attached to it. I'm using no objective lens in the Zeiss Ultrafo 3B, and am using what is called a pH position, bringing in a Bertrand lens, and I'm focusing with the Bertrand lens to bring out the details. Gives me the lowest power in the microscope, so I can bring the specimen totally into the field of view that one is seeing here. It's a very small but highly convoluted specimen, so it takes many forms of light. The cesium iodide, 2 incandescent bulbs on the left and the right-hand side. Now we'll move to a higher level of magnification of this and see what we will find. We're looking at this specimen now with Nomarsky interference contrast. The objective is a 8x pole, so we're between 80 and 120 diameters magnification. Under interference contrast, one sees now a vein of highly birefringent material running through the specimen we did not see before. What I'm pointing out is that to see the details in this specimen requires an extensive use of all the tools of microscopy. Now we can see banded structures in the center of the field, like full lines as one would encounter in lava-like flows. The material looks like it has been extended in a flow process, but it does not show what one would see in a furnace from extensive heating. The remark has been made that this specimen was made by a cold flow process. And this seems to be the case here, because one finds areas of structure which are highly birefringent, as one sees in here, very distinct lines. Here is a complete pattern of material flowing in and precisely stopping. Here one can see a better detailing of this. It's like a material has been kneaded and rolled over and flowed together. Here's another band. There you can see a good view of the structure now on the surface. I'm putting the analyzer in, rotating it. We'll go now from the quartz iodide lamp that we're using here, 100 watt to a 250 watt cesium iodide. Much more detail is evident, and one gets better penetration of the light into the sample. Coming back, we're conscious of it, but now we can clearly see it. I will examine this specimen later on with infrared and ultraviolet microscopy to look for further detailing. This is pure exploration, because one does not know what one is dealing with at this time. We'll go to one more level of magnification. We'll go to a higher magnification in this particular area and see what we will see. Here is the same area now at 160 diameters, and one can clearly see distinct areas between in the specimen. If one were to use gross examination of the specimen, one would lose the significance of these discrete areas. In the analysis we will do now, we will take each one of these areas and examine them in detail. Go to a higher level light source. Suddenly these things come out in sparkling detail. Reducing the field diaphragm. Adjusting the aperture diaphragm. There's the edge of the diaphragm. Quite difficult in. Here we are. We'll move around a bit. And little tiny crystallites. These banding are fascinating. Here it is here. There we are. What I'm trying to visualize is how this thing is put together. There are discrete bands of material you saw in the lower part, and they look like they've been manipulated instead of made by nature. With this now, we will conclude with this specimen. We're now looking at a silvery metal specimen number 5 in the 4th stage of development that is used according to the document that was given to me in the preparation of the metal for a spacecraft. We're looking at the object now, which has been mounted and polished under cross-field polarized light using a 250-watt cesium iodide light source. There is birefringent areas in the middle of the picture, and as we rotate the analyzer, we'll see the specimen of the metal appear here. It is rather complete in the sense that there are no precise differences in grain boundaries. There are occlusions in the material which are quite birefringent, especially around the edge of the metal. As one rotates the analyzer now, one can see these strongly birefringent areas. As the thin skin of a crystalline-like material, highly birefringent, white as one can see here, and the metal itself has minute specks of also birefringent material in it. These must now be analyzed by the scanning electron microscope. We're dealing with a rather low magnification. In this case, it is the 6.3 X-pole, so we're about 100 diameters. We'll go now to higher magnification. We're now at 1,600 diameter magnification, and now a whole new world appears in this specimen under polarized light, cross field. There are structures within structures that one sees, very, very unusual, and which now bear investigation. At lower magnifications and without oil, one just sees a metallic surface. Now one sees a structure which is composed of various type of interlacing areas. By the use of television, we can get a isodensitric value showing these areas, and as I rotate the analyzer, we overload the Vidicon to see these areas. Now we're coming in again. Look at the center of the screen and you will see these areas start to evolve. Here they are. Now by use of the Vidicon tube, here they are being brought out. These are structures within structures. This is very exciting, very interesting, and bears looking into. This is the polished specimen. We're at Crossfield. We're using the 251 xenon cesium iodide source. We go to higher magnification yet, and higher yet. We're now at over 2,500, and one can see these birefringent structures. Very exciting, and we must go now to the scanning electron microscope. This is very unusual for a metal to have these birefringent areas. A metal normally will not exhibit this. The birefringent areas are the white portions and the deep bluish areas that we're seeing on the color screen. I'll expand this. Now, we'll move on to other specimens. We'll scan for a moment. The edge again. This is the edge. It's the highest magnification one can go now in the optical system. And from here we must now go to the scanning electron microscope.
This is the letter that was sent to me by Mr. Wendell Stevens, and I indexed each of the type of specimens with a code number. The photomicrograph under low power is shown here of the specimen, and I've taken and given to each discrete area a index number. Magnification is 8 diameters. The physical specimen was almost identical in dimension to what you are seeing here. Very much alike. This is another specimen. Now, we took under polarized light and examined. This is under just reflected light coming in at an oblique angle. Very interesting thing is the goldish area here, there's silvery, but also these peculiar flow lines coming. I then went and used Nomarski interference contrast microscopy, and we came across now crystalline patterns, which are in here. And again, you notice these flow lines, like a material being melted and pulled out like taffy. This is very unusual to see a metal specimen exhibiting these type of both composite crystalline patterns and metallic luster of a piece of metal. But even more interesting, I started to go now into this area here, then using what we call polarized light. We polarized light and going to a little higher magnification, only 63 diameters, we got to highly birefringent areas. These colors are caused by the optical rotation of your light, giving you these intense colors, which we call birefringence. And circular areas, little deposits of crystalline formations in these circular areas. Now, I decided to go, being I saw that it was what I call a composite, means it is composed of a varying grouping of materials. I had to go to discrete form of analysis, not just general analysis or even cutting a piece out, but I had to leave the specimen alone and study it piece by piece. And that was done with the Hitachi scanning electron microscope. I work now with an associate of mine, Dr. Wee, and this is now a scanning electron micrograph of A1 area, and this is A2. This is 500 diameters. This is now this area here blown up to 2,000 diameters. This is a field emission microscope, so one gets then very, very high degree of depth of field. The specimen was not touched, which means I did no gold plating, no metallization of the surface, so it was left alone. And what excited me was a tremendous ability to get a depth of field in the specimen without ion burning. In other words, the electron beam did not accumulate. These surfaces acted as conductors here and gave us then a very sharp, clear delineation of the picture. Normally you have to take and cover this with gold, to get a sharp picture.
This specimen is called number 4, same metal as the sample that turned to powder, dark third process. The silver is the 4th process and the gold silver is the 5th. The preliminary identification of this is copper, nickel, and silver. Silver solder, which is used for many forms of welding, is a combination of silver and nickel. Now the specimen that I'm talking about is right here, and this is the specimen that we're talking about right here. The other lines that one see are the fracture lines from the embedment material and the cracking that took place. We'll go into polarizing the light. And now one gets a lot of the glare away, and one can see this specimen is dark, but there are, again, I call your attention to these lines, these vertical lines. Now we're going to look into that center part, that whitish area, and this line will increase the magnification and see. We're now viewing at Nomarski interference contrast at around 50 diameters. We see these highly birefringent lines, flow process, and again, a series of vertical lines. We'll go to now polarized light and see what further detail. Here's some other areas. This is the boundary of this small particle. To give you an idea of dimension, we'll put a scale in to appreciate the dimension of this sample. These two lines here represent 1 millimeter, 1 thousandth, 1 millionth of a meter. And as one takes this away, one sees the specimen below. It's not very big. Again, these whitish areas around the specimen showing that there was an interaction taking place between the plastic and the material. We'll go now to a higher magnification and polarized light. We're now looking at the specimen at 63x with a pole objective. The analyzer is out. One can see a small speck of the material. It's blackish in color, and because of the light now we polarize the light. There's the extinction position, and one can see there is a structure as I rotate the analyzer slightly. It's tied in there. We'll move in different areas. Here's the edge. Here's a reaction from the edge of the specimen forming highly birefringent material. Again, these spots, which we see before, here is a complete distinct area. Pull the analyzer around. We're in the metal. Here we see it. This is the boundary of the plastic. We're into the metal area here. This is number 4. This is the boundary in the plastic. Rotate the analyzer. We can bring it out. Here we are. There are 2 distinct areas here. These are the marks in the center of the picture again for Vickers hardness measurements. You can just see them. These were done in Switzerland. This will be reported on separately.
In this crystalline area, the predominant element was silicon, which is this band here, and iron, and there was a secondary band of sulfur, which is right here. These were very, very intense bands, and we did not attempt to go through the analysis of all the other particular lines that were present. We just took the 3 main ones, and we stopped there. We moved to another section, and I will come back here to this area. And now we were going into this plane right in this region, and we found evidence of what looks like mechanical manipulation. One sees now discrete marks in a diagonal form in this direction and marks in this direction. But what is exciting, it looks like it's been plowed. In other words, a pressure, and there is a scarfing on either side. And you see the regular spacings of these. And I was just working a space group out here, and they're very regular. We did an analysis of this area here. Now we're at 500 diameters. The elements that we found were totally surprising. The major element, which is shown here, was the rare earth metal thulmium, Thulium. It was totally unexpected, with a very small trace down here of bromine. This minute bump down here was a combination of argon and silver. Now, the remarkable thing that we noticed was that, yes, we got this band here. This was the only one that matched in the spectral analysis in the computer, but the secondary bands that are connected with it were not present, which meant that it was a very pure metal, but the secondary emissions were not present.
The 5th stage of development, this is sample number 6, mounted in a whitish plastic, which they were used in the final development of the spacecraft. The indentation marks are Vickers indentation hardness measurements that were made before in this specimen. We will see these as we go up in magnification. To give you an idea of the size of the specimen, I will put a marker for identification and measurement purposes. We have now in